Hello everyone and welcome. We are excited to present to you today's webinar on eUSB2 V2 Elevating USB Connectivity for Low Voltages, brought to you by TrueChip's USB team. Here's our agenda for today. We will start with an overview of eUSB2 V2, then discuss the reasons why it's needed. We will explore the performance advancements, its application, and the differences between eUSB2 V2 and eUSB2 V1. We will then focus on TrueChip's VIP for eUSB2 V2, including its block diagram and key features. And finally, we will touch upon a sanity test case to demonstrate its practical application. Now, let's first discuss about eUSB2 V2 overview. eUSB2 V2 is an abbreviation for Embedded USB 2 version 2.0. It offers a low voltage PHY that can deliver a 4.8 Gbps symmetric or 4.8 Gbps/480 Mbps asymmetric signaling rates. It is an ideal high-performance enhancement to eUSB2 native mode to provide more bandwidth for peripherals such as embedded cameras by adding significantly higher data rates to USB 2.0 while maintaining a low-voltage electrical interface. eUSB2 V2, introduced in 2024, which is a major leap from its predecessor eUSB2 V1, which was introduced in 2021. eUSB2 V2 standards represents the latest iterations of this technology, delivering significant advancements in data transfer speeds, power management, and data integrity. It also achieves a good balance between data transfer rates and its cost. eUSB2 V2 targets embedded platform use cases where large fan-outs are not needed because the total number of embedded peripherals will tend to be small. In addition, the distance available with a single physical link is sufficient for typical mobile platform embedded use cases. An eUSB2 V2 device may be a redriver or peripheral. Following is the bus topology of eUSB2 V2. Here you can see that the eUSB2 V2 root hub port supports eUSB2 V2 redriver and peripheral. Also, it does not support eUSB2 USB2 repeater and eUSB2 V1 peripheral. Now we will see the need for eUSB2 V2. First one is I/O power efficiency. As power efficiency becomes increasingly critical in today's computing devices, there is a need for I/O technology to be optimized for both active and idle power. USB 2.0 technology, originally optimized for external device interconnect, is primed to be enhanced for inter-chip interconnect such that the link power can be further optimized. eUSB2 is introduced to improve both the link active and idle power efficiency. Second one is bandwidth requirement. USB 3.x technology is used to address the bandwidth need. It is not an optimal solution for these camera devices because it is a symmetrical link offering the same bandwidth capacity to both downstream and upstream traffic. For a camera device, bandwidth requirement is asymmetrical. A USB 3.x camera is not an optimal solution for embedded application. Hence, we required eUSB2. One of the major need for eUSB2 V2 is process scalability. Meantime, silicon technology continues to scale, device dimensions are getting smaller and therefore more devices can be packed onto a single integrated chip. However, the device reliability challenge arising from the densely packed transistors has become more profound. The manufacturing cost for an advanced process technology to support 3.3 volt I/O signaling has grown exponentially. A low voltage USB 2.0 solution is therefore required to address the gap. Hence, it provides a low voltage USB 2.0 PHY solution to eliminate 3.3 volt I/O signaling requirement, which allows the process technology to continue to scale for many generations to come. Another need is implementation simplicity. The PHY analog content is reduced. Digital mechanisms are employed for PHY functionality, for example, device disconnect detect. Now we will see the performance advancements in eUSB2 v2. First one is data transfer rates. eUSB2 v2 is an extension to eUSB2 native mode that targets onboard peripheral interconnects, providing HSSX speed, which is symmetric operation where the link is operating at 960 Mbps to 4.8 Gbps in both transfer directions. Second one is HSUX speed, which is asymmetric operation where the link is operating at 960 Mbps to 4.8 Gbps in the upstream direction and 480 Mbps in the downstream direction. Next one is HSDX speed, which is asymmetric operation where the link is operating at 960 Mbps to 4.8 Gbps in downstream direction and at 480 Mbps in the upstream direction. Second advancement is reduced burst turnaround time. Only inbox applications are supported, hence minimizing peripheral interconnect propagation times. It enables shorter interpacket delays and also don't support external operations. The illustrated diagram is of eUSB2 v2 channel topology. Since we know eUSB2 v2 is intended to support inbox applications in native mode, so the physical channel is relatively simple with both the host and the peripheral being inside the system's physical boundary. An external cable or connector is not supported. However, an internal cable and connector is allowed. One major performance advancement is reduced electromagnetic interference and radio frequency interference. To minimize EMI and RFI concerns with potential data sequence that may be periodic is scrambling. Scrambling is required for all the packets in both directions. The scrambling function is implemented using a free-running linear feedback shift register LFSR. Next advancement is flexibility in power consumption. eUSB2 v2 features advanced power modes to adapt to various system requirements, optimizing energy efficiency as it works on low voltage of 1.2 volt. Burst. eUSB2 v2 defines a burst mechanism that modifies the isochronous protocol by allowing a single in or out transaction to transfer up to 3 data packets, thus improving throughput by eliminating burst turnarounds within a burst. Increased max packet size. Bulk endpoint max packet size is increased from 512 bytes to 1024 bytes. It also provides higher bandwidth, the ability to allocate more than 3072 bytes of bandwidth per microframe. Now, let's talk about the applications of eUSB2 v2. One of the major applications is embedded camera. An eUSB2 camera can send data to the host at 4.8 Gbps but receive data from the host at 480 Mbps. It is used in various embedded systems such as microcontrollers, sensors, and IoT devices. It is also used in automotive, in vehicle communication for infotainment systems and diagnostics. It's also used in consumer electronics such as smartphones, tablets, and other portable devices. Here are the few major differences between eUSB2 and eUSB2 eUSB2 operates at 480 Mbps to 4.8 Gbps in both symmetric and asymmetric link, whereas eUSB2 works at 480 Mbps in symmetric link. eUSB2 only supports native mode, while eUSB2 supports both native and repeater mode. eUSB2 bulk endpoint max packet size range from 512 bytes to 1024 bytes. On the other hand, bulk endpoint max packet size is of 512 bytes in eUSB2 Isochronous transfer supports burst transaction up to 3072 bytes per SI, whereas eUSB2 don't support burst transaction. Hub is not supported by eUSB2 while in eUSB2 hub is supported. As embedded systems become increasingly complex, ensuring the reliability of interfaces like eUSB2 is paramount. To help you achieve this, TrueChip offers a comprehensive verification IP solution. Let's explore how it works. This diagram illustrates the architecture of our eUSB2 VIP. At its core, it's designed to simulate, test, and validate your eUSB2 design. Let's break it down into key components. First, we have the compliance test suite. This provides a library of pre-written test sequences based on the eUSB2 standard, as well as a powerful constraint random test suite. These suites ensure your design adheres to the specifications and handles various scenarios effectively. The heart of our VIP is the verification engine. It consists of two crucial parts, the eUSB2 host BFM and the eUSB2 device BFM. These act as virtual representations of the host and device in your system. They simulate the communication between them, allowing you to observe and verify the behavior of your eUSB2 design. To ensure accuracy, we have the eUSB2 scoreboard. This component acts like a referee, comparing the actual communication with the expected behavior and flagging any discrepancies. Additionally, the eUSB2 monitor captures all the transactions on the bus, providing valuable insights for debugging and analysis. Finally, we have the USB interface representing the physical connection between the host and device. This shows the EDP and EDM signals which carry the data between the components. Now, let's take a look at TrueChip's eUSB2 VIP features. Our VIP supports symmetric operation where the link is operating at 960 Mbps to 4.8 Gbps in both transfer directions, and asymmetric operation where the link is operating at 960 Mbps to 4.8 Gbps in the upstream direction and at 480 Mbps in the downstream direction. or where the link is operating at the 960 Mbps to 4.8 Gbps in the downstream direction and at 480 Mbps in the upstream direction. It supports increased maximum size of bulk packets when operating with eUSB2 v2 compliant software and more efficient isochronous transfers to improve transaction efficiency. It supports the disconnect or connect in extended high-speed signaling at native mode. It also supports protocol extended token transactions for LPM ACK handshake. TrueChip's eUSB2 v2 VIP supports all operations such as host reset, low power states, resume, remote wake up, disconnect signaling between host and peripheral device. It supports scrambling and descrambling of data to minimize EMI and RFI concerns with potential data sequence that may be periodic. It provides support for eUSB2 v2 bit stuffing operation. It also supports link power management LPM L1 and suspend L2. eUSB2 v2 supports HSX sync pattern and EOP of SOF. It also supports UTMI and UTMI plus parallel mode. It also provides support of link power management LPM L1 and suspend L2. And it also provides support for XHCI functionality on host model. Our VIP supports 15 in and 15 out and one control endpoint for each device. It also provides detailed activity log file for individual layers for easy debugging. It also supports dynamically configurable modes. It provides a strong protocol monitor with real-time exhaustive programmable checks. Callback support in all layers. It also provides supports to configure protocol timers and intentional error masking. On-the-fly protocol checking using protocol check functions, assertion checks for UTMI interface. It gives built-in coverage analysis. Also, it provides graphical analyzer to show transactions for easy debugging. Now, let's take a look at the logs and waveform of our eUSB2 v2 VIP, which we have generated by running a bulk-in test case to demonstrate the flow of data across host and device. Let's begin with device enumeration. This is the crucial first step where the host controller discovers and configures the connected eUSB2 v2 device. We start with power on and reset. This ensures the device is in a known state, ready for communication. Next, the device responds with default address, for example 00. At this point, the device is operating at its default address, allowing the host to communicate with it before assigning a unique address. We then move to the set address stage. Here, the host assigns a unique address to the device, establishing a specific communication channel. Following the address assignment, we have the get device descriptor step. This is where the host requests the device basic information such as vendor ID, product ID, and device class. This information is critical for the host to understand the device capabilities. We then move to get complete device descriptor. This step retrieves more detailed information about the device, including its supported configurations and endpoints. Finally, in the enumeration phase, we have the get configuration descriptor. This provides the host with information about device supported configuration, including power requirements and interface settings. This completes the enumeration process, ensuring the host is fully aware of the device capabilities. After enumeration, we move to set configuration. Here, the host sets the appropriate configuration for the device based on the information obtained from the configuration descriptor. This includes selecting the desired interface and setting up the endpoints for bulk-in transfers. Now, we get to the core of the bulk-in transfer. The host initiates the data transfer by sending an in token. This token signals to the device that the host is ready to receive data on a specific endpoint. It's essentially a request from the host to the device, "Send me data." In response to the in token, the device sends data. The device sends a valid data packet to the host. This packet contains the actual data that the host is requesting. We verify that the data packet is correctly formatted and contains the expected data. Finally, the host acknowledges data. If the host receives the data packet correctly, it sends an ACK, which is acknowledgement, to the device. This confirms that the data was received without errors. This acknowledgement is crucial for ensuring reliable data transfer. If the host detects an error, it may send a NAC, which is negative acknowledgement, or stall, indicating that the data needs to be retransmitted or that the endpoint is halted. By following this detailed flow, we ensure that the eUSB2 v2 implementation is robust, compliant, and performs as expected. Now, here you can see the generated waveform for the bulk-in test case. First state is port reset state. It is generally used only after the eUSB2 port is configured to be either eDSPN or eUSPN. An eUSB2 port may be default to eDSPN or eUSPN upon power on, or configured to eDSPN or eUSPN after power on reset. After that, port configuration is done, which is a handshake defined to initialize connection. Then the connect state is a state where the eUSPN is attaching to its eDSPN. After connect state, there is reset state, in which both eUSPN and eDSPN are waiting for or performing a USB 2.0 bus reset and high-speed negotiation, respectively. After that, device acknowledges by sending device chirp K. Now, the set address request has been sent. Following that, eUSB2 v2 specific sync pattern has been sent, which is 40 bits long with the first 24 bits of consecutive Ks followed by 7 pairs of Kj and ended with 2 Ks. After set address is done, we can see the host request for the basic information of device supported configuration and endpoint and sets the appropriate configuration for the device. In last, we can see that the bulk-in transfer has been done, in which the bulk endpoint max packet size is of 1024 bytes. Thank you very much for joining us today. We hope this webinar has provided valuable insights into eUSB2 v2 and TrueChip's eUSB2 v2 VIP.